Section: Introduction. In this section, we highlight how human intelligence is characterized by metacognitive skills, especially self-regulation, which allows us to recognize our limitations and seek help when necessary. By acknowledging uncertainties, we can ask for assistance before facing failure, which helps avoid costly mistakes and builds trust. However, despite advancements in large language models, LLMs, many AI agents still lack this metacognitive awareness. Overconfident agents can make serious errors, while those that ask for help too often can be inefficient. Ideally, an AI should assess its uncertainty and ask for help selectively to ensure reliability and effective use of human resources. We face challenges in training an agent that requests help within a limited budget. We need to find the right moments to ask for assistance, balancing reward design and policy optimization. If we encourage too many help requests, we risk exhausting our budget too soon, while not encouraging enough can lead to missed opportunities for help. Creating effective reward functions is complex and often requires extensive training and adjustments. Additionally, generating annotated data for supervised training under budget constraints is resource-heavy, as the space of possible actions is vast, and even human annotators can struggle to determine the best times to intervene. We also question whether we can collect intervention data once and reuse it across different budget scenarios, and whether we can manage the number of interventions during training. Even if we train a policy to stick to a budget, controlling intervention use during training is crucial. To tackle these issues, we propose a hybrid framework that gathers intervention data in one go and combines deep scoring functions with traditional reinforcement learning, RL. Our method consists of 3 steps. First, we collect state transitions with randomly triggered interventions to approximate how the environment behaves and learn process reward models for both the main actor and the intervention. Next, we use tabular dynamic programming with these models to find optimal action sequences that stay within budget, iterating until we reach our target without needing to retrain the policy for each reward setup. Finally, we fine-tune the helper policy using the annotated data, allowing it to make smart intervention choices within budget limits. This offline approach significantly cuts down on costly intervention calls during training and enhances robustness by using both process reward models and tabular RL. Our empirical results show that our method, which utilizes powerful models and test time computations as interventions, performs comparably to systems that intervene at every step but requires far fewer interventions. By training LLM agents to self-regulate and seek help wisely, we move closer to reliably deploying LLM-based systems. In terms of related work, we note that recent advancements in LLM agents have led to AI systems capable of handling various real-world tasks in open-ended settings. Most prior research has focused on supervised fine-tuning for tool use or applying RL in well-defined tasks. Our focus, however, is on using RL techniques in environments with unclear instructions, specifically addressing how to enable agents to request help, which is central to our work. Regarding AI safety, previous studies have often concentrated on aligning AI systems with human values and ensuring robustness against attacks. However, these aspects alone may not ensure safety in critical situations where an agent's limitations could lead to serious failures. Thus, we frame our work within the broader concept of trustworthy AI, which emphasizes the need for agents to perform tasks reliably without unintended failures. Lastly, we discuss self-improvement in LLMs, where past research has looked into enhancing model responses through feedback and critiques. While these methods typically assume the model can solve the task, we recognize that when a task exceeds the model's capabilities, intervention from more capable models is necessary. We also explore confidence estimation and metacognition, noting that agents aware of their limitations can better guide human trust and seek external knowledge. While previous methods for estimating confidence have their limitations, we propose using a process reward model with tabular RL to adapt flexibly to different budget constraints without needing extra training. Section Summary. In this section, we discuss the importance of metacognitive abilities in AI agents, emphasizing the need for them to recognize their limitations and request assistance judiciously to avoid costly errors. We propose a hybrid framework that efficiently collects intervention data and optimizes policies under budget constraints, ultimately enhancing the reliability and performance of LLM-based systems. Section: Task and Setup. In this section, we describe our task and setup using the situated instruction following, SIF, task. This task involves locating objects, interacting with people, and completing household chores in unpredictable and changing environments. We believe SIF is an excellent benchmark for assessing how well agents powered by large language models, LLMs, can manage complex and uncertain instructions. The uncertainty arises because the speaker's intent may not be clear, and humans can change the environment, like moving objects or relocating themselves. Even advanced models, such as GPT-4o, find these tasks challenging due to these ambiguities. Our setup ensures perfect visual perception, allowing the agent to receive descriptions of the environment at each step. The agent can perform actions like, go to room X, or explore room X, creating a multi-turn, text-based environment suitable for LLMs. Despite having perfect perception, agents must adjust their understanding of uncertainty to interpret unclear instructions, deciding whether to gather more information, search other rooms, or clarify the instructions. We utilize two types of tasks in SIF. The first, PNP, is a simple pick-and-place task. The second, S_OBJ, is more complex, involving vague human hints, limited visibility, and the potential for objects to be moved. We have 1,000 training tasks and 40 validation test tasks for each type. To achieve reliable agent behaviors, we focus on two main strategies: self-regulation and requesting interventions. Self-regulation allows the agent to autonomously stop the task if it believes it cannot succeed, conserving resources and ensuring reliability. Requesting interventions involves the agent asking for help at specific points during the task. We use two base actors, GPT-4o Mini and Llama 3B. The Llama models are trained on trajectories from GPT-4o and GPT-4o Mini for the S_OBJ and PNP tasks, respectively. For interventions, we employ three types: a simple Monte Carlo tree search, MCTS, that generates candidate actions, more powerful models that enhance the base actors, and oracle trajectories for task-specific interventions. We first examine self-regulation, asking whether an agent can stop a task if it feels it cannot complete it. We measure the difficulty of a state by calculating 1 minus the probability of success from that state to the end. To facilitate self-regulation, we train a process reward model, PRM, using trajectories from our base actors, fine-tuning a Llama model on state outcome pairs to learn the probability of success. To evaluate self-regulation performance, we identify the highest difficulty encountered in a trajectory before the final step, using this to optimize accuracy on a validation set. Our results show high precision and recall, indicating that the PRM score effectively reflects the probability of success. Next, we explore whether the PRM thresholding strategy for self-regulation can also apply to multi-step intervention requests. We consider a process with states and transition probabilities, where each state has a probability of leading to success. Unlike self-regulation, multi-step interventions occur at each step, and the intervention can come from a more capable model or an oracle. We analyze two settings: state-wise interventions, where help is applied selectively, and task-wise interventions, where help continues for the entire task once a state is identified. Our findings reveal that for task-wise interventions, PRM scores effectively identify tasks needing assistance, similar to self-regulation results. However, state-wise interventions consistently outperform task-wise ones, suggesting that targeted help at difficult states is more effective than blanket assistance. We also discuss the limitations of PRM thresholding for state-wise interventions. When an intervention temporarily reduces difficulty, the base actor quickly resumes control, leading to a cycle of toggling between the intervention and the base actor, which hampers performance. This highlights the need to consider transition dynamics when identifying states that require intervention, rather than relying solely on difficulty measures. Section Summary. In this section, we describe the situated instruction following SIF task, which challenges agents to navigate uncertain environments and interpret ambiguous instructions while performing household tasks. We focus on strategies like self-regulation and intervention requests to enhance agent reliability, employing models like GPT-4o Mini and Llama 3B, and we evaluate the effectiveness of a process reward model, PRM, in guiding these strategies, revealing that while PRM scores can indicate when to self-regulate, they are less effective for multi-step interventions without considering state transition dynamics. Section. Method. Requesting targeted interventions. In this section, we discuss our method for requesting targeted interventions. We recognize that deciding when to seek help can be difficult, especially when we have limited resources. While a probabilistic roadmap model, PRM, can estimate the chances of success, it doesn't account for how our requests for help might influence future outcomes. This highlights the importance of understanding transition dynamics. To fully consider state dynamics, difficulty, usage, and help-seeking strategies, we need to explore both rewards and policies. However, implementing a complete deep reinforcement learning (RL) process for optimizing rewards and policies can be very time-consuming and resource-intensive. Additionally, gathering data for training policies can be costly and limited, raising the question of how we can efficiently collect and reuse data across different budgets while managing the number of interventions. We propose a method that is both offline and hybrid. It requires only one round of data collection for training and combines a learned PRM with traditional tabular RL. This approach allows us to keep our usage, meaning the number of interventions used during inference, within the specified budget while determining the best policy for requesting help at non-terminal states. The main components of our method include transition model collection, dynamic programming for usage, policy iteration, reward search, and final training. Our method has several benefits. First, the dynamic programming step is very quick, taking only minutes without needing GPUs or extra intervention requests. We do not need to train the policy for reward search. We can simply repeat the fast dynamic programming process. Second, since our method is offline, it can adapt to different budgets. We only need to collect intervention data once, which can then be reused for various budgets. Third, combining learned PRMs with tabular RL improves robustness and avoids the inefficiencies associated with deep RL. We also define our reward structure. Agents can request help at non-terminal states to improve their chances of success while managing help costs. Our goal is to maximize the success rate of tasks while limiting the number of interventions to less than a specified cost. In this context, we outline the rewards. If help is requested, it incurs a negative reward, while not requesting help results in no immediate reward. Success at terminal states gives a positive reward, while failure results in no reward. We derive the usage policy iteration algorithm, which is similar to value iteration, by breaking down the value function into success and usage components. Unlike standard value iteration, our approach is offline and integrates PRMs for more robust classical RL. The value function for an optimal policy represents the expected return from a state under our reward structure. We can separate the value function into success and usage components, leading us to a recursive definition of optimal usage and policy. This process converges to a unique fixed point, allowing us to determine the optimal policy by deciding whether to request help based on the calculated thresholds. Section Summary. In this section, we propose a method for requesting targeted interventions that balances the need for help with a constrained usage budget, utilizing a hybrid approach that combines learned probabilistic roadmaps, PRMs, with classical tabular reinforcement learning, RL. Our offline and efficient usage policy iteration algorithm allows us to optimize intervention policies while reusing data across different budgets, ultimately enhancing robustness and reducing training costs. Section. Algorithm. In this section, we provide an overview of our algorithm for calculating the fixed point m star of r and pi star of r. The process starts with gathering a table of transition dynamics. We then use these dynamics along with a learned PRM to iteratively switch between reward search and policy search until we reach our desired solution. In Phase 1, we explore and build our transition model. We gather transitions by randomly triggering interventions using the base actor on training tasks. For each transition, we update our counts. Specifically, we conduct 3 rounds of rollouts with different probabilities for triggering interventions, ranging from 0 to 1. For tasks with multiple interventions, we collect transitions for each intervention separately and for various combinations of intervention probabilities. After this exploration, we normalize the raw counts to estimate transition probabilities. In Phase 2, we perform offline dynamic programming for iterative reward and policy search. We look for a cost parameter R that fits within our usage budget constraint. We can systematically search for possible R values and, for each candidate, run a quick offline dynamic programming to get the expected usage and the corresponding policy. We initialize our usage estimates and iterate through our calculations, comparing the expected usage with the budget and adjusting R as needed. This iteration is efficient and does not require new environment rollouts. For usage computation, we calculate the expected help and no-help values for each state based on the transition probabilities. For policy computation, we determine changes in policy and usage. If the change in usage is very small, we default to no help. Otherwise, we compute the ratio of changes to update our policy. We repeat this process until we meet our convergence criteria. From the converged values, we derive the optimal policy and expected usage from the starting state. We compare the expected usage to our budget and, if necessary, adjust R and rerun the offline dynamic programming. This allows us to quickly resolve for multiple R values without needing additional data collection. In Phase 3, we finalize our policy training through supervised fine-tuning. We train the helper model to replicate the decisions of our derived policy for deployment in downstream tasks. This helper model is then evaluated on a test set. Section Summary. In this section, we outline an algorithm to compute the fixed points m**r and pi**r through a 3-phase process. First, we explore transition dynamics by collecting data from interventions. Second, we perform offline dynamic programming to iteratively search for a cost parameter, R, that meets usage constraints. And finally, we train a helper model using supervised fine-tuning to replicate the derived policy for deployment. Section. Extension to multiple interventions. In this section, we extend our algorithm to handle multiple types of interventions, each with its own budget. We can apply the same framework from earlier sections, making adjustments to accommodate these individual budget constraints, which vary in cost and expected usage. Essentially, we adapt our second phase to choose actions that minimize the total cost across all interventions. We present results for our method using the Llama base actor alongside improved model and MCTS interventions. We integrate our trained helper to initiate interventions when needed. For comparison, we use random state selection and the PRM state selection as baselines. Our main results, shown in a table, compare our method to the baselines based on success rate, path length weighted success, task execution length, observed intervention usage, and expected intervention usage. We calculate expected usage by averaging the starting states under the optimal policy. This expected usage metric is unique to our method, as it is not easily determined for others. We train our approach with different reward scales, leading to varying intervention frequencies. Remarkably, we achieve performance close to a policy that always intervenes, using significantly fewer interventions on average. For instance, in the S_OBJ task, we attain a success rate of 62.5% with just one intervention on average, surpassing baselines that use similar or more interventions. Our expected usage closely aligns with observed usage, particularly for lower intervention counts. While discrepancies arise at higher reward scales, our expected usage still provides a good estimate, allowing us to set budgets based on training data without extensive evaluation. We observe that performance drops at high reward scales are primarily due to the base llama actor, which struggles with out-of-distribution states and invalid actions. This issue accounts for most failures at high rewards but is minimal at lower scales. We do not see these problems with other interventions, likely because their strategies align better with the base actor's training distribution. In our analysis of multiple interventions, we utilize our Phase 3 extension to assign individual budgets. We present results with various configurations for the Better Model and MCTS. For baselines, we randomly select states for each intervention. Our method consistently outperforms these baselines, achieving higher performance with fewer interventions. We find that using multiple interventions does not significantly improve results compared to a single intervention under similar constraints, likely due to conflicting strategies. However, our method still surpasses multi-intervention baselines. Additionally, our expected usage remains a reliable predictor of actual usage, especially at higher reward values, aiding in budget selection. In a qualitative example, we illustrate an S_OBJ task where our helper approach, using MCTS-based interventions, effectively navigates a cluttered environment to locate a stuffed toy. The base actor struggles and gets stuck, while our helper identifies the stall and calls for timely interventions, leading to successful task completion. Section Summary. In this section, we extend our algorithm to handle multiple intervention types, each with distinct budgets, allowing us to optimize intervention selection while minimizing costs. Our results demonstrate that our method achieves high success rates with significantly fewer interventions compared to baselines, effectively utilizing expected intervention usage as a reliable predictor for budget allocation. Section Analysis. In this section, we focus on the important issues of coverage and robustness when collecting offline and tabular states, particularly regarding unseen states. We examine how different selections of training data, specifically different outcomes from the decision process, affect the performance of our helper model and its intervention usage. We compare two strategies for using the outcomes from the decision process as training data for the helper. The first strategy, called All States, includes every state action pair from the optimal policy for all states collected in the first phase. The second strategy, Trajectory Only, starts from an initial state and follows the optimal policy, using only the state action pairs from that specific trajectory. If the optimal policy encounters a state that hasn't been seen before, we do not include that trajectory for training the helper. We evaluate these strategies based on how we split the training set into seen and unseen tasks. Seen tasks are those that end after following the optimal policy, while unseen tasks occur when the optimal policy encounters a new state. It's important to note that we do not have the optimal policy available for validation or test sets, as the decision process focuses on finding trajectories, so this splitting only applies to training tasks. Under the Trajectory Only method, we find that the helper policy struggles with unseen tasks, resulting in high intervention usage, low success rates, and a significant gap between actual and expected usage. In contrast, the All States approach shows better alignment between actual and expected usage, along with higher success rates. We believe that broader sampling in the first phase could further enhance performance for unseen tasks.